Greetings, everyone. Time to talk about limits again. We just got through talking about multivariable functions. So the next inevitable step moving towards calculus topics is we need to have limits. Okay, so if you're rusty on your limits, then go ahead and jump over to my Calc 1 series. I have a couple of quick little things that you can recap if you'd like, or just go read up on your limit laws, whatever it takes, okay? But we need to have limits so that we can also talk more about derivatives and integrals later on as well, right? Also, continuity is going to come up in this section. All of these things, we have to have the language of limits. Okay, so the language actually is not going to change very much. It's just more like the thought process behind the limits. You need to upgrade a little bit, okay? Give it a limit 2.0, if you will, right? So here's the old definition. It's still the definition of limits back from your first calculus course, okay? A limit of a function as its variable approaches some value is equal to some output value. Don't forget the L right here is some output number from a function. And the limit is the measurement whether or not that function is approaching that same value, right? So there's two different things in saying the L is the output of F and L is the limiting measure as X approaches something of F, okay? So what this language means is that if I pick any epsilon gap around the output, then I can always find some delta size gap around the input. So that's the limiting process, right? If I let my sights hone in one size at a time, right? If I keep decreasing and getting closer to an output value here, right? I keep letting epsilon get closer and closer and closer, and for every single one of those epsilon sizes, I can find a delta size, and they always include the A value. Then that means that is the actual limiting value, right? The Y values will approach L as the X values approach A, if you will, right? On this particular function here. Okay, that's what this is saying. The distance from the actual function value to the value of L is less than some epsilon, implies that I should be able to find X within some small distance of the A value that we're trying to approach, okay? This limit then fails if I ever can pick an epsilon as I'm getting closer where maybe those delta gaps don't include the A value on your axis anymore, right? So if, like, for example, if your function is broken or if the function value is way off base or whatever, and you're trying to limit in the wrong spot, right? So these epsilons would be up in a weird place, and then the deltas would be not surrounding your A value there. But this was the whole process that we had. We called it the epsilon delta proof method for limits, right? And basically what this was useful for is if you ever get to a limit that was too difficult to look for a pattern for, or it was too weird to have, the value didn't make sense, or something like that, okay? But actually the definition of it here is really used for making all of those limit laws that you just take for granted most of the time, right? For example, a lot of the limits that you do, you just end up plugging the numbers in, right? All of those are the limit laws saying, hey, as long as this thing is all connected and everything and it all works, you can just plug numbers in. All of those are proved from this definition. So you start with this definition, and then you can use all of those limit laws as long as you have this backing it up, okay? So back in Calc 1, I would have told you that there's the three levels of limits with the proof kind of off to the side. Level 1 is if it's easy to plug in and no problems, you just plug in. Level 2 is if something's happening that's not letting the limit work when you plug in, maybe there's something you can simplify, like factoring and reducing and rearranging and maybe using conjugates, things like that, right? There's sort of a middle level there where if you can fix it, go back to level 1 and try plugging it in again, right? And then there was the bottom level. If the limit flat out doesn't work and you can't get any sort of pattern out of it, then you just start making the number pattern out of it, right? Okay, well, we're going to upgrade to multivariable here, and what's going to happen is level 3 is going to go away. Okay, here, let me show you why. We're not going to be able to do numerical patterns like you did with the limits here, because notice on this one, I come from the left or I come from the right, and those are just the two patterns that you would put in a little chart. If you couldn't do the limit any other way, you'd sit there and plug a bunch of function values in from the left or from the right. Okay? Let's look at the multivariable version. You'll notice a lot of the language is the same. I still have to have any epsilon on the output. There must exist a delta somewhere in the input. But remember what the domain of a multivariable function is, right? Specifically on a 3D function, in other words, a 2 input variable, 1 output variable function, right? A function of 2 variables. The domain is a section of the xy plane. So there's not just a left and a right anymore. You have a point on the plane, and you can come at that point from all different directions. And as if that wasn't, complicated enough, you don't have to approach it in a straight line. The way I have it written here, look, this is the point in question that you're letting the xy approach AB, right? So in the domain, I'm approaching this point from any direction in the plane. I don't have to approach it in straight lines. I could also approach this with a sinusoid if I wanted to, or I could approach it with a parabola if I wanted to, okay? You don't have to approach things in straight lines when you're in this plane. You just have to say, as it approaches AB, the point, which is to imply all directions and all paths that lead to AB, okay? So this limit is doing more than just a left and a right now, right? So that's where stage 3 is now gone. We're not going to be doing numerical patterns from left and right. There's going to be too many paths to try. There's an infinite number of them. There's no way to do those number patterns anymore. So we need to rely on our limit laws. We need to rely on a lot of inequality stacking methods also. And then at the end of the day, if it comes down to it, we may actually have to go through an epsilon delta proof in order to show that a limit does exist and is equal to a value. Okay? So we have the same kind of definition. Let's just run through it here. Every epsilon, remember that's an output gap, right? Then I must be able to find some delta that the input is only that far away from the point that we're approaching. Okay? So right here, the distance from the function to L is less than epsilon. That's the same idea as it was in the other one. Our output is still just one variable, and if you pick some L value for your limit, epsilon is going to be the amount that your output is closing in on it, right? So you can start with a big epsilon, whatever, but then every epsilon all the way up to right on top of it, right? For every single one of those epsilon values, I should be able to find a corresponding delta. Now here's where it's a little different, because over here, delta was just how far left or how far right. Here, from your point on the plane, imagine a circle, right? And as the epsilon closes in on the output value, delta is the size, the radius of your circle as it closes in on the point AB in the domain. So as you close in on your output, right, you also should be closing in on your input from all directions, hence the circle with the radius, okay, and all paths. So you have this circle of radius delta, and it's really the same calculations, right? You see how you have your distance from L is less than epsilon? Same thing, right? Function distance from L is less than epsilon. Implies that I should have some delta such that the distance from the input is less than delta. Same thing here. I should have some delta such that the distance, that's the distance between 2 points. Do you notice? Square root x minus x squared plus y minus y squared. But it's not just any two x's and y's. AB is the point that we're interested in approaching. And x and y right here is going to be all points within this radius. Okay? So I'm talking about x and y picking all of the points that are going to be within this circle. Okay? So it's all points x, y less than delta that make this true. Right? Okay. So it's basically the same idea as far as domains and ranges go, but the higher consideration is there's no longer a left and a right. Okay? I can approach the AB point in the domain from multiple directions and with multiple paths. Okay? So if I'm testing a limit, I have to keep into consideration that there's no longer a left and a right. I have to specify a path if I'm going to look at individual directions. Okay? There's going to be an overall limit, but then also, like over here, I would have put a plus or a minus for a left and a right. With these limits, I can also say do this limit along this path, right? But you actually have to now specify some sort of path in the domain, which will be some sort of line or parabola or sinusoid, whatever path it seems necessary to use for your limit. Okay. Good news is, because this structure is pretty close to the same as this, it's almost identical. It's just an upgrade with the distance here, right? And the domain is a bigger dimension. Okay. Since it's pretty much the same, all of those limit laws are still the same as well. All of the proofs for the limit laws done from this work exactly the same with this, because we're still basing it off of distances in the domain and distances in the range. Okay? So your limit laws, like the limit of a sum is the sum of limits, or the limit of a product is the product of the limits. You can split the limit up to individual pieces, and you can do the limit inside of compositions and stuff like that. All of those limit laws still hold true, okay, for your everyday limits, right? And then that sort of links to continuity a little bit. So keep in mind, the only time that limits are going to get interesting is when you start having funky points in the domain, divisions by zero, square roots of negatives, all kinds of those things, okay? So don't overthink this. A lot of the ideas that you had for limits are still valid. But on the special limits that you're going to need to consider, you need to upgrade your thinking as far as how the domain is working and how we have different paths. Okay? So let's get the ball rolling by starting with some limits that would bring back some old memories and start you off at the basically level 1 here, right? At the top level. So like I was saying with the definitions, all of the limit laws are still valid. So whether it's y times ln x plus 1, or if it was all just x times x, if it was nothing but x's, the limit laws work the same way. The limit of the product is the product of the limits, right? I can take this limit and do just y, and I can take this limit and do just the ln of x plus 1. I can take this limit and do just the 2x minus y, and so on, okay? And the reason all of that works is because of the way each of those individual pieces is simple, right? That was basically the gist of all of your limit laws. If the pieces are all simple enough that you can plug the value in, then the limit also agrees with the function value. That was basically the main idea behind all of those limit laws, right? So for example, the limit right here where the xy is a point from the domain approaches negative 3,7 from all directions and all paths of the function y ln x plus 1 over 2x minus y. To be honest with you, taking the limit at this point, unless it's for some special meaning or project or whatever, the limit itself is almost overkill, right? Because this function is only going to have problems where either the limit doesn't exist or where the denominator is divided by 0. And crap. Start all over. Okay, so let's get started with some limits that'll bring back some old habits with your limits, right? Just using the normal limit laws at locations for limits where the points are simple, right? Basically, the gist behind your limit laws were that the limit can spread to each individual piece kind of like a distributive property, as long as all of your pieces were simple and well defined at those points. Right? That was the main idea behind having those laws. So right here, I'm just going to notice real quick, this is stage 1 for all of your limits. Try to plug in the numbers. If I plug in -3 for x and 7 for y, right? If I just start by putting those values in, so let's see what happens, right? Okay. So I'm saying that it would be 7, right? ln of -3 plus 7 divided by 2 times -3 minus 7. So what would we end up with? We're going to have -13 in the denominator, and then I'm going to have 7 ln of 4 in the numerator. And it all works out. All of my functions are well defined at each of those points, right? And I don't have any domain issues at the given points. A domain issue in this case, right, would have been anywhere where x plus y gives me a negative value for the logarithm or 0, and anywhere 2x equals y so that the denominator would equal 0. But this isn't either one of those types of points, right? So by all my limit laws, I'm able to just go ahead and plug it in, and the limit and the function value actually agree there, which, as you remember later on, we're going to define with continuity. Okay, let's try again. If I take 0, 0, and I plug it in for each of the values, I've got 0 plus 3, 0 plus 0 minus 1, not causing anything crazy in that arena. So I'm going to end up with 3 over -1, or -3. Right? That's the limit laws. Stage 1, as I would always call it, in all the things you might have seen me in, or if you've had my class before. Right? Stage 1 is try plugging in the numbers. Those are the limit laws that we went through all that trouble proving in Calc 1 and then reiterating in the last scene. And this is why we have them. Right? If you can plug them in and everything is well defined, then it works. Okay, next. The limit as xy approaches 0, 0 of x squared minus y squared over x plus y. Well, if you plug in 0, 0 on this one, look at what happens. I'm going to get 0 minus 0 over 0 plus 0, which is 0 over 0. Right? If you think back, we had a name for that. It was an indeterminate form. Okay? That doesn't mean it's automatically undefined, right? The function value is undefined though, right? Remember that for later when we want to talk about continuity. The function value is undefined because of the division by 0. But remember, the limits are designed to look at the function without actually having to go to that point. So I can't apply the limit laws here. In other words, I can't, just plug in the numbers and get the value here, right? But I still have stage 2 up my sleeve. Is there a way that this can be manipulated so that eventually I could actually use the limit laws with something that it is equivalent to? Because It's not going to be equivalent at the point 0, 0, but that's the lovely part of limits. It's not actually at the point 0, 0. We're approaching the point 0, 0 from all different directions. So any simplifications I do would be valid at the other points around it, right? So here's what we do. We go total stage 2, and I start doing my limit as xy approaches 0, 0. And I look for some way to simplify this. Well, I can factor the numerator. X minus y times x plus y, and the denominator is still x plus y, which allows me to reduce. And so I am left with this being equal to the limit as xy approaches 0, 0 of x minus y. And remember, this wouldn't fly if this was just the function, okay? Because the function itself is not equal to x minus y at 0, 0. The function is undefined there. But the lovely part of this being a limit is we're not at 0, 0, so I can actually do this simplification. And then when I plug in 0, 0, I just get 0 minus 0. So the value of my limit is equal to 0. 0 minus 0 is 0. Okay? Okay, so think about what that means. The function is not defined there, but every path from every direction, as it gets close to there, the function value wants to look like it's going to hit 0. Okay? All right, let's try again. The limit as xy approaches 0, 0 of x squared plus y squared over square root of x squared plus y squared plus 4 minus 2, right? Okay, so if I plug in 0, 0, always try your limit laws first, right? If I plug in 0, 0, 0, 0, I get 0 on the top. I have 0 plus 4 in a square root, which is a square root of 4, which is 2. 2 minus 2 is 0. So yet again, I'm getting the 0 over 0 indeterminate form. Okay? So remember, that still means there's hope. If it was some number over 0 or something else crazy like that, then we may want to start considering undefines and infinities. Also, it could be bad news, right? 0 over 0 being indeterminate means it may exist, it may not exist. Try something else first. Okay? So, right here, what I'm going to do is I'm going to look at this and say, is there a way that I can handle making this simpler? Maybe doing something with this radical. And then you should be like, hey, wait a minute. We always get rid of radicals with conjugates, right? And I'd be like, yeah, let's use a conjugate. So I'm going to multiply the numerator and the denominator here by the conjugate of this denominator. So that's going to be square root x squared plus y squared plus 4 plus 2. Right? The conjugate is where you just change that sign. So, when I do this multiplication here, I'm still left with a limit, right? Because this is a stall tactic. I'm not performing the limit yet. And then I have x squared plus y squared times square root x squared plus y squared plus 4 all plus 2 divided by. Now, remember, when you multiply something times his own conjugate, all you get is the first term squared minus the last term squared, because the cross terms are going to add out to 0. So the first term squared is just x squared plus y squared plus 4. And then the last term squared, negative 2 times 2, is minus 4. Right away, you should be seeing the domino effect that's about to happen. Plus 4 minus 4, those add to 0. And then I've got my entire denominator here is x squared plus y squared. And then I have the same thing multiplied right here. So these are going to reduce. Now that it's simplified, Remember, the function wouldn't be equal to this, but the limit can. So now try the limit laws. Plug in 0, 0. And notice what we will get is the square root of 4, which is 2, plus 2. So the value of my limit is now 4. Okay? So a lot of the ideas behind limits, especially on these first few, should be the same. Is it something that I can plug in? Is it something that I can simplify? Let's take a look at that last one we just calculated. It's the function x squared plus y squared over square root of x squared plus y squared plus 4, and then minus 2 still in the denominator. It's this bowl shape right here. As you can see, it looks completely connected and filled in. But remember, when we were looking at the limit, whenever you plug in 0, 0, if I actually try to do that, you're going to see it's undefined, right? The function value is not defined there, right? It's division by 0. GeoGebra doesn't know how to graph that, though. There's no hole there, although technically there should be. Right? If we were to draw this by hand, we would actually put a hole in the graph right at that bottom point right there, which is right above the 0, 0 point here, right? However, if you look from all directions, this thing is completely symmetric. And no matter which direction I were to come from, whether it be a straight line or a parabola or whatever, if I were to follow any of those paths, they would all lead to this same point right here, which has a z value of 4. So therefore the limit does exist and gives a value of 4. Now let's look at a couple of limits that do exist, but not obviously right away, okay? So let's start with the limit as xy goes to 0, 0 of the ln of x squared plus y squared. And there's one of your rotated shapes, right? It's got the x squared plus y squared. Imagine the ln function, right? Something that approaches that y axis and uses it like a vertical asymptote and then hooks outward and then rotate it, right? That's basically the kind of shape we're talking about with this function. But you remember, ln of 0 is not defined. However, we do have a limit of that, right? Okay, now you got to be a little bit careful here, and you got to be making sure that you're doing something that does actually stay on the general side of your limit and your limit laws and your factors. I can't plug in the 0, 0 right now, okay, so I can't use the limit laws. I can't simplify this any kind of way either, right? So the stage 2 is out. Well, I have other tricks now that we're in multivariable as well. One of them is I could try converting into a different coordinate system to see if that simplifies the limit from being multivariate, right? In this case, if I switch to polar, right, because remember my domain is the xy plane, which I can do rectangularly, or I can do in a polar fashion with r and theta. If I convert this into polar, then I'll have the limit as r goes to 0 of the ln of r squared. Why can I get away with this on this particular function, you say? Am I still keeping true to what we said about limits earlier? And the question is yes. The answer to the question is yes. Because I do actually still have a limit that's involving two variables here, okay? But what I'm saying is that theta is not actually contributing to the limit in that way, but also what I'm saying is not only am I approaching the center by letting r go to 0, but it doesn't necessarily have to be in a straight path, even though r does move in straight paths. I'm not saying anything about theta because theta can do whatever it wants to do, right? It was just x squared plus y squared. The actual function itself does not depend on theta. It's a rotated object, right? So from any theta direction and from any combination of theta directions, it can do whatever curve path it wants. R is going to 0 from all directions, okay? So then when I do that, when I convert into polar, notice I can then do the ln of r squared, which is really just 2 ln r, right? So I can do this. And now it's back to basically a one variable limit in some light, right? And we know the answer to this limit. It's negative infinity. Okay? Now remember, negative infinity is not actually a number. I can't say that it's a function value, but the limit is telling me the trajectory, the predicted direction, the predicted measure of the function. And it's also thought of as a pattern. So in this case, the limit of this function is telling me that it has some sort of vertical asymptote there at that point where from all directions, it's going to try and go to negative infinity. It's going to hug the z-axis all the way down, but never actually intersect with it. Okay? So sometimes converting to a new system can help on a few cases. Now, another thing that we can come up with is we can do sort of a nested limit. It's an interesting little side parlor trick for limit goers here. And the idea is that if a function is approaching some limit value, right, or should I say it this way, because the z, right, if the function values are approaching some L, then why couldn't I say the function minus L is some other function, a of x, y, or closely related to it in any way, and then say that that limit of that new function is going to 0. Because that's what's happening, right? The function should be approaching some value L, and as the function gets close to L, the distance from it is supposed to go to 0. Okay? And this is actually very true. If I can show that the difference between a function and the limit value is less than some function, all right? Now notice this is an absolute value, so it's always positive, okay? If I can show that that is less than some function and the limit of that simpler function, that's the idea, right? I go from something complicated to something simple. If I can show the limit of that simpler function is just 0, then that means this distance is going to 0, which means this function should be going to L. And therefore, if this limit is 0, then this limit is equal to L. If you're looking for a proof, it's in the direct statement here, right? The limit of the distance function basically is what you can think of it as, or just simply compare it. The a function for this limit is going to be less than some epsilon, and for every one of those epsilons, this function has to have a delta when it's closing in on its distance, right? It's the same set of points as the other limit is interested in, right? So as the domain points get closer, these two limits are basically following each other in any path, any point, whatever. And we've already stated that a is less than epsilon. But this is less than a. So this would also be less than epsilon when inside of this particular delta-sized disk. Okay? So basically, it's like we're putting a limit inside of a limit. And since this one's working and saying that the distance is going to 0, then the overall limit is getting closer to L. Okay? So what does this boil down to? If I have something kooky like this, okay, then what I do is I try to think of what the limit should be. Well, it looks to me like since we're putting zeros in here, right, I've got a 0 times a 0 in the numerator 3 times, right? Whereas in the bottom, I've just got a couple of squares, which is at best 0 2 times, okay? Let me go over that again. I have a 0 squared, and then sine of 0 is also 0, right? So the numerator is like 0 cubed, or as it gets close to it, something close to 0 cubed, right? Whereas in the denominator, I'll just have 0 squared added together with some, coefficient as xy goes to 0. So the numerator is going to be stronger here, which tends to make you think, oh, well, this is going to go to 0, all right? So I tender a guess. Equals 0. There's another way you can come to these guesses, okay? You could try picking a path, like what is the limit as xy goes to 0, 0 along the path where y is 0, right? So if I let y be 0, then I've got 0 over 3x squared, which is 0. So there's your first guess if you plug in one path. Or what if I do it along the path where x is 0, right? If I do the path x is 0, right, then I've got 0 over y squared basically, so it goes to 0. Or what if I'm going to 0, 0, what about the path where x equals y, right? Then I would have y cubed over, I'd have 4y squared here, right? And then the y squareds would reduce, okay? And then you basically would just have y times sine y, which would give you your 0 in question, right? So, well, no, you just have sine y, which would go to 0. So, as you can see, as I keep picking different paths, I keep getting a value of 0, right? And those are just lines. Of course, I can't do just lines, so I need some proof in a general way. So I'm going to try using this. I'm going to say, I think the limit is 0. So then the function itself minus the limit value that I'm guessing would need to be less than some simpler function. Okay? Well, that's not too difficult to do. This is minus 0, right? So here's what I'm going to do. I'm going to do 3x squared sine y over 3x squared plus y squared. Minus 0 is just itself, right? Okay. However, I can say that this is less than or equal to, bear with me, this. How can I say that that's going to be true? Well, we're saying that y is some number and it's approaching 0, right? The squared makes it always positive, and then I'm adding it in the denominator. Think about it for a second. What happens every time you make a denominator bigger, right? 1 over 2, 1 over 3, 1 over 4, 1 over 5. Every time I make a denominator bigger, I make the overall value smaller, right? So if I'm adding y squared in the denominator here, this overall value would have to be less than if I didn't add y squared. And the only time the equal would be true is if y is equal to 0, right? Then those two quantities would be equal. Okay, but then notice this. If this is less than this, but without that y squared there, I could actually reduce this a little bit. So what I'm actually saying is that 3x squared sine y over 3x squared plus y squared, now it's the absolute value of this thing, is going to be less than or equal to the absolute value of sine y. Okay? Now I don't need to worry about the absolute values, but they do have to be there for the inequality to be true. I can take the limit of this, right? The limit as y goes to 0 of the absolute value of sine y. Now I could actually say xy, but I don't need to, right? Well, just for formality, I'll go ahead and say it. As xy goes to 0, 0, right? Of this, well, that's just a quick plug-in now. I'm back to my limit laws again. The limit as y goes to 0 of sine y is sine of 0, which is 0. So I've proven this part. I've shown that my function minus its limit value is less than some function, and the limit of that function goes to 0. Okay, not just any limit, the limit around the point that I'm interested in. So, this was all I needed right here. The fact that this limit goes to 0 means that this distance goes to 0, which means this limit goes to whatever my L value was. In this case, it just also happens to be 0. Okay? Don't let that fool you. Because it could have actually been any number for this limit, and I would just do the function minus that number, and then I would just do some sort of other simplification. If there was some other number there, I may have combined the like terms with common denominator or something like that, and then found some way to simplify the fraction into something easier to deal with in a limit. And then you still just show that that limit goes to 0, and then whatever this limit value was, if it was 10 or 20, whatever, would be the limit if I could prove that part. Okay? So there are other little side avenues that we can use where I don't have to think of doing it in different separate paths, and I don't necessarily have to go all the way down to always using the epsilon delta either. Okay? So we have other avenues and side theorems for these things. So real quick, let's take a look at those two functions that we were just talking about. The solid of revolution, ln x squared plus y squared. Just like we were talking about, it's like if you took a ln function, right here you can see the shadow cross section of it right here. And if you just rotated it 360 degrees around the z-axis, it's exactly what you get. And notice, as in true ln form, it does actually go to negative infinity the closer you get to 0. And it does it completely radially too, if you look at it that way. If you stare down the barrel, you can't see past the plane there, but look at the bottom half of it right here. You can see it definitely from all directions does the same thing. So that's why it was so easy to convert into polar coordinates and then have such a nice limit as a result. Next, we looked at 3x squared sine y divided by 3x squared plus y squared. It has this sort of pinched sinusoid look to it. You can see the cross sections on one side of it are just sine functions basically, and the other cross sections look sort of partially parabolic or almost rational parabolic. We get a wrinkled sheet basically. Okay, but the point of interest was as we approach the origin 0, 0. So if I zoom in there, right, you can see that from all directions it does actually approach this point in the center. And technically there shouldn't be a point there, right? Because plugging in 0, 0 does cause a division by 0. So the function doesn't actually exist there. But the limit does exist, as we were able to show. And the limit does go to 0. So it does actually hit the 0, 0, 0 point there, as you can see. It just skips over it, basically. And again, GeoGebra doesn't know how to graph a hole in the function because it doesn't know how to draw something the size of a point. And it's highly technical, and it's not going to just put a little hollow ball there, because technically that would include other points too. So it just doesn't draw any kind of hole whatsoever, and we have to already know that, of course, it's undefined there. Here are a couple of examples of some limits that don't work. They're undefined. Ironically, they're less work than the ones that you have to prove equal a value. You almost want these crazy ones to not work sometimes just to make the problem easier. Although it is more interesting when the limit does work and it has some sort of meaning behind it. These examples, I mean, since the limits don't work, it's like you're not getting as much out of the problem. At least you're not putting as much work into them to get that little bit of information. But anyway, I digress. the limit as xy goes to 0, 0 of y times tangent x over 3x squared plus y squared. Now remember, just like in Calculus 1, a limit fails to exist for many reasons, but one of the main ones is whenever two different directions don't give the same limit measurement. And in a lot of these cases, all you have to show is that there is one example of something giving two different measurements, right? It's the other way. It's whenever a limit does exist, you have to have it from all directions and all paths. That's sort of hard to show, right? Because I can't do the exhaustive method on that. But with these, all I have to do is show a counterexample, which is at minimum two directions, right? I'll just pick two different directions and maybe there'll be something different, and then all of a sudden the limit is proven to not exist because you have one example of two different measurements, okay? So like I said, at least two directions have to, you have to measure two different ones to show a disagreement. You may have to go through 3 or 4 or 5 before you find a disagreement, just depending on how crafty you get with your method of selection of a path to follow. Okay, so here we go. On this one, let's start by doing the limit as xy approaches 0, 0 when, let's just do the path when x equals 0, right? Now remember, the domain is a set of points x and y, okay? So here it's like I'm looking at a picture of just the domain. Imagine the surface is coming out at you, and it's some, surface here. And the point that we're interested in is hovering right over the point 0, 0 here, okay? So when I pick x equals 0 as my path, then what I'm talking about is only following the axis here, wrong axis, only following the axis here, the y-axis, like this. I'm going to basically be letting x equal 0, and I'm going to be following along this direction here. Well, I guess technically it could be also this direction here. But we usually assume the positive one, right? I'll be coming along this line is what I'll be doing. So when x equals 0, then really this limit downgrades to as y approaches 0, because x is already at 0. So then I get tangent of 0, I get 3 times 0 squared, like so, right? But tangent of 0 is 0, right? So I get an overall value of 0, because it doesn't matter what all the other things come out to be. It's going to be times 0 and divided by some other number here, right? So I'm going to get 0. Well, what do I get when y equals 0? So in other words, when y equals 0, I'll be following along the x-axis, right? I'll be walking along this path right here, like that. So whatever the surface is, right, I'll be following that curve this way. On the curve would be like a path on the surface until it gets to that point. Okay, so that's going to be limit as x goes to 0, because y is already at 0, and it's going to be 0 times tangent of x over 3x squared plus 0 squared, because y is already 0, right? And again, I get 0 times, doesn't matter what the number is, it's going to be 0 over some number, right? I'm getting 0 as that goes along. Well, so far we have agreement, right? I haven't disproven anything yet. I haven't proven anything either. I would have to do an infinite number of paths and an infinite number of directions before I could do the exhaustive method. That's just not possible. Okay? So I just got to keep picking because I'm really got a feeling that this one shouldn't exist. Okay? And part of the tell on that one, by the way, is the fact that the numerator's kind of like a squared. It has two variables, multiplied. The tangent doesn't exactly work like that. But then in the bottom, I've got the squares, and I'm getting like a 0 over 0 here, but there's nothing to reduce, right? That's sort of how I'm getting the feeling of that. All right. How about when y equals x? There's another linear path. And by the way, you don't have to choose linear paths. I could pick a parabolic path, like when y equals x squared, or I could pick a sinusoidal path, y equals sine x. This time we just chose when y equals x. So that means that I'm going to be approaching 0, 0 like this, along the line y equals x. Okay? And then whatever pathway that happens to be on the surface that's coming out at you, right? I'll be approaching the point over that along this line only. Well, if y equals x, I have the limit as xy is going to 0, 0. But really, instead of xy going to 0, 0, y is equal to x. So instead of this, I'm just going to say let x go to 0, because if they're equal, letting one go to 0 is taking care of both of them. And y equals x, so everywhere I see a y, I'm going to put an x. X tangent x over 3x squared plus x squared. So that's going to be equal to the limit as x goes to 0 of x tangent x over 4x squared. Well, I can reduce this, right? I can take an x here and an x there, and that's going to leave me with tangent over 4x. Let me split this up a little bit differently for you. Like this. It'll be 1 over 4 times 1 over cosine x times sine x over x. Whoops. What did I forget? I forgot my limit. Limit as x goes to 0 of all this. Look at what I did. I split tangent into sine over cosine, sine x over cosine x. The 1/4 is still there, and the over x I put underneath the sine x. Why do you think I did that? I hope that you recognize that limit, right? It's probably been a little bit, but that's an important one. The limit as x goes to 0 of sine x over x is 1. The limit as x goes to 0 of cosine x is a plug-in. That one follows the limit laws, right? I can just plug in 0, cosine of 0 is 1. So I'm getting 1/4 times 1 times 1. Answer to this limit is 1/4. Okay? So there we go, disagreement. I picked a different path, and all of a sudden I get a different value for the answer of this particular limit. Therefore, this limit does not exist. Okay? So let's look at this next example here. Same idea. I'm going to prove that this limit doesn't exist by approaching it from different directions. But there's a little trick that I have, a little method that I have here, where you can do many directions all at once. You just have to know what you're looking for. Okay? So right here, with this limit, what I'm going to do is I'm going to approach when y equals mx. Now you got to be a little careful here, okay? Because I picked specific numbers with these two especially, and then this was a special case, all right, that went through this point. If it wasn't 0, 0, I would actually have to shift my line a little bit here to make sure that it goes through the point in question. Okay? But this one will work because it still goes through 0, 0. Okay? If it went through something else, I would have to do y minus whatever equals m, x minus whatever. Okay? So y equals mx. The thing about what I've actually done here, though, I've let m be a sort of variable here, right? I'm not picking a slope yet, and what this is doing is allowing me to have all of the slopes represented with the letter m, okay? All I really need is just 2, right? Because I just need some sort of disagreement between two different versions of a line, right? Or I could pick y equals mx squared even. You know, you could pick whatever path, but this is basically checking all of the different slopes from all of the different lines simultaneously. I just need to be able to simplify it and argue that the answer shows that I would get some disagreement. Okay? So let's get there and I'll show you what I mean. If I do this substitution here, y is based on x, right? So the limit really becomes as x goes to 0, because if x goes to 0, so will y. And y is equal to mx. So I'll have x times mx plus mx to the third all over 2x squared plus 5 times mx quantity squared. Okay? Now I'm just going to start doing a little bit of algebra simplifying this here. So I have mx squared right here plus m to the third x to the third over 2x squared plus 5m squared x squared. All right. So now everything is comfortably in its spot and simplified exponents. Let's go one step further. Do you notice that all 4 terms loosely, right, have at least an x squared? What I'm going to do is I'm going to divide the top by x squared and the bottom by x squared. And what that's really going to do is really, value-wise nothing. It's 1. And everything can divide by x squared here. So it's just going to get rid of, trim some of the fat for you. Trim out the extra pieces that we don't need. I'll have m plus m cubed times x, because that's the only one that had x to the 3, divided by 2 plus 5m squared. And now look, limit laws. I can plug 0 in for x, no problem, right? Whereas in the very beginning, if I plugged in 0, I'd get something 0 over 0, indeterminate, right? Here, limit as x goes to 0 just affects this piece, because everything else doesn't have an x. So this piece goes to 0 with the limit. So what we have for our limit value is m divided by 2 plus 5m squared. Okay, great. So Mr. Simon, when you picked a path and you got a limit answer, doesn't that mean the limit exists? No. Because look really carefully. This is not just one path, remember? It's all of the linear paths that you can imagine, except maybe not when m is undefined. I mean, probably not doing that one. But y equals mx represents almost all of the paths of lines. There's an infinite number of paths that I've just checked here. Okay? Each one has a different value of m. So pick 2 of them, like m equals 1 and m equals 10, whatever. That means you'd have to plug in 1 and you'd get a certain value, 1 over 7, right? But if you put in, say, 10, you'd get 10 over 502, right? You'd get different answers to this limit with different values of m. So different linear paths would give different values. What we've just shown is that because m is in the answer, then all of these paths disagree. Therefore, this limit doesn't exist. So if you were looking for an answer that the limit would exist, then you should have been looking for a solid number answer from this path. And that actually wouldn't have been enough. It would have been an indicator, hey, this limit might exist. Might. But no, that's not what we got this time. This time, m is in the answer for this path, which means all the different directions are getting different answers. Every single value of m different gives a different answer to the limit. So they all disagree. It's a huge room of disagreement from all different directions. And that's just the lines. We didn't have to check any of the parabolas and other stuff because m is in this answer, right? It's not just a number, all right? This is undefined. All right? Now let's take a look at these two interesting functions that we just found those special limits of. First, y times tangent x over 3x squared plus y squared. Brace yourself. It has a lot of asymptotic type features because of the tangent part of it. So take a look, even just from the sideways portion, you can see how it's spiking at certain regions, but it's more like a planar type of asymptote rather than just a line, because sometimes the one side goes down and the other's up, and then on the other side over here they've swapped, you see. This side is up and now it's down. Okay, so it's there are some planar asymptote pieces in there, and that's because tangent is solely based on x. Whenever x is one of those values like pi over 2 or 3 pi over 2 that make tangent undefined, you're getting like an entire sheet of asymptotic points. So anyway, the point that we were interested in, of course, is as it goes to 0, 0 here. And as you can see, even the features there are pretty interesting. It has these weird hills on either side here, and then it looks like it comes from underneath on either of the other sides here. And the way we talked about the limit was we took it from different directions. So here, let me zoom in a little bit so that you can get the full effect of that here. Okay, so look, if you're looking at it from the XY plane, this is the way it should look right here. This is the positive x, here's the positive y, and the first curve we did was where x is 0. So that's this line right here that just darkened, as you can see. So then, if I look at the graph, notice it completely stays on the axis the whole way. And therefore, if I were following just this line, it would look to me like the limit was 0 right there at the center. And same thing. With y equals 0, I'm following just the darkened axis here, as you can see. And again, if I were following just that line, you can see that it would look like it should be at a height of 0 on the z-axis. Okay, but then that last line that we took was the line where y equals x, right? So here's the domain region here, right? Here's the line y equals x. There it is right there. But then what curve does that trace out on the actual surface? Take a look. What curve does that trace out? It looks like a weird hybrid of some tangent pieces and one of the secant type of pieces right here in the middle, right? You can see that U shape right here is kind of like a secant, whereas these swirlies are kind of like tangents. Again, in the domain, take a close look. It's the line y equals x.
But when you have that z value in there and you're actually looking at all three dimensions, you can see that the curve is actually disjoint, right? It is separated at these asymptotic planes. But more importantly, look at what's happening as x and y go to 0. Look, it's above right here. It's actually hitting right there, and you can see the marker right here is a half. So it's actually hitting at a quarter, just as we predicted right there. The function itself, of course, is undefined there, but the limit right there, well, technically the overall limit's undefined. The limit of just this curve, though, is the 1/4 mark right there. So just as we said before, since these two limits hit 0, right, you can see that they both hit at the 0 marker, but then this curve is above them right here. It disagrees. So therefore the limit can't exist. Next, we also talked about this function right here, xy plus y cubed over 2x squared plus 5y squared. And what I've done is I've extremely zoomed in. As you can see, it's 0.2, 0.4, 0.8, so on, 0.6, 0.8, so on. So it's really zoomed in here, closer than a single unit, because I wanted you to see the wrinkle in the sheet. Do you see how it looks like somebody's grabbed the middle and just pinched it in different directions? You can see where it looks like it's been pinched here. Of course, you can't see that from the domain view, right? This is the XY plane. But then when you actually get the Z values in there, you can see the pinch. And therein lies our problem with the limit here. Because if I follow the limit along some of these lines, you can see where they'd want to hit the center of the pinch. But if I follow the crease along this ridge here, it's going to want to follow the top of the pinch, not the middle. So you can already see it, I hope, that different directions are going to give different limit values. But just to really hit that point home, what I've designed is a slider here that will show you all the different directions that we talked about. So right here, if I hit this line, just notice this is the line with a -10 slope in the XY plane. Makes sense, right? And if I zoom it in, look, you can see it's definitely not going through 0 there. You can see it's just missing it there, right? It's going through a point that's just underneath 0. Okay? Now watch what happens as I set this thing in motion. Okay? First of all, in the domain, if I set this thing in motion, watch what happens. As I change the slope, right, you can see the line rotating. Right? You can see the line rotating. And that's basically what's going to happen here. Okay? Now, let me speed it up just a little bit. Okay. So, watch the value of where this thing is hitting there as I turn this on to do the different lines. You see it rotating, right? You see it rotating? But as it's rotating, look at where the line is hitting the axis, and then all of a sudden it changes, right? What's happening is, as it's rotating, it's going across this ridge. Here, watch it again from a different perspective. Let me rewind it for you here. And then watch it from the perspective of what it's doing on the ridge here. So watch, the line slowly follows the valley in this thing, and then as it keeps rotating, it comes back up that ridge right there. So right when m is 0, let's see if I can get it. There we go. It's in the middle there, right? When m is 0. And then as it continues to rotate, look, now it's at the top of the ridge there. So I'm getting different values at every single different line there. So not only is it a discrepancy between two different directions, every single linear direction has a different value that it wants to hit. And you can see that as this line sort of floats around inside of the graph there and hitting different values.
Okay, so we got the limit language for multivariable functions. Let's talk about the next inevitable step, which is continuity in multivariable functions. And this idea is exactly the same as continuity in single variable functions. It boils down to this one equation. If the limit as our input goes to a certain domain value of the function, right? The limit of the function at a certain domain input equals the same thing as the function value calculated at that domain input, right? So if that limit equals the function value at every point in the domain, basically, we have continuity. And then, of course, you can talk about continuity on small sections or an entire domain or an entire system or space, whatever. Okay? Just all of the collection of points where the limit measured is equal to the actual function value, which is going to be most of the points, right? All of our limit laws are exactly this statement right here. I can plug the point in most of the time just to get the value of the limit. Okay? So really, when we're talking about discuss the continuity of a function, we're really saying, hey, find those few rare points where it's not continuous, because pretty much everything we study is mostly continuous, right? Find those few places, and they're usually pretty blatant, like logarithms of zero or negatives, or square roots of negatives, or division by zero, things where they mathematically just fail outright, or some of those indeterminate places where you get 0 over 0, right? Those are possible discontinuities as well. And remember, there's two different kinds of discontinuities, right? There's removable and non-removable. The removable kind is usually a singular point, something that you can easily just replace a location with a function value of your choosing using a piecewise function. Okay? Those limits are the kind of limits that exist, but the function does not. Okay? But remember, with continuity, there's several levels of this equation that can fail your continuity, right? First, the limit has to exist. Next, the function also has to exist. And then lastly, they have to be equal, right? So there's some little stages in there. So continuity can fail. Most of the time, there's two main reasons. Either the limit doesn't exist, or the function doesn't, or is not equal to the limit, right? It's not as common for the function not to equal the limit unless it's already separated in some sort of piecewise function or whatever. Most of the time, your discontinuities come from either there is no function value or there is no limit value, right? And if there is no limit value, obviously the whole function thing's out the window anyway. Okay, so let's look at a few examples. Discuss the continuity of this function x squared minus y squared over x plus y. We did this limit earlier, remember? The limit as this went to the point 0, 0. Take a step back and just look at it, right? If I take a step back and just look at this thing here, there's going to be a whole place where this thing is discontinuous, okay? But then there's also some of the iffy places on this thing, right? Okay, so this thing is not defined as a function when x plus y equals 0, okay? So whenever you're discussing continuity, your first step should be, let's talk about the domain, right? So the domain of our function, here is the set of all points such that x plus y doesn't equal 0. Okay. Now, of course, there's other versions of this guy right here that you can talk about, right? Basically, x can't equal negative y, right? That's our domain. We have a set of points in all of the R2 plane, right? And x can't equal negative y, okay? Now, of course, if x does equal negative y, can I still take the limit of this thing, right? That's the real key here. Can I still take the limit? Well, we did one limit. We did an example of when x and y were equal to 0. We did 0, 0. Well, what about the limit at 1, negative 1, or negative 3, 3, right? All of those would be on that line, x equals negative y, okay? But I would still approach the limit the same way, because in every single one of those, I would get a 0 over 0 indeterminate form, right? So the limit exists at all of these points, right? The limit exists at all of those points. I can actually do the limit along that line, right? We can do the limit along. I hate to say along x equals negative y, because technically it's not along the line, but the limits at points on x equals negative y, right? We're going to end up doing the same trick that we did earlier. We're going to end up factoring like this, right? And reducing. And so we're going to end up with x minus negative x, basically, right? We're going to end up with 2x. So here's the thing. The limit value exists at all of these points, but they don't exist in the domain, okay? I can do the limit at any of those points by just following the reduction rule and then using our limit laws. That's like a parlor trick. I can wave my hands and make the limit work. But remember, limits don't make continuity by themselves. The limit exists, but function value cannot exist there, because at the end of the day, the function is this object. And if you plug in any of these points, you're getting a division by 0. Okay? So the domain is this, and also the domain shows where it is continuous at. Okay? So you can actually say f of xy is continuous on its domain. Right? All points x, y, such that x is not equal to negative y. And the reason is because the function values don't exist. Okay? The limits do exist. Remember what that means. This is a removable kind of discontinuity at each one of those points. I would just have to use a piecewise function and reassign where those domain values go, right? In the case of this one, they're undefined, but I could easily set up a piecewise function that says, hey, whenever x equals negative y, just output 2x. And then all of a sudden it agrees with the limit and you'd have continuity, right? But just with the piecewise function, this thing by itself, hopeless at those points, right? It's only continuous on the domain points where it does exist. Not for lack of the limit trying, though, right? Okay, right here. This one, when we write out his domain, kind of the same effect, right? I'm getting that division by 0 thing going on here. His domain is, again, the set of all x, y's, such that 4x can't equal y, right? I'm getting that as my domain here, because anytime 4x equals y, I'm going to get a division by 0. That's this line here. However, this is a different kind of discontinuity, okay? This is the same answer as the previous one. It's going to be continuous everywhere else. Continuous on this domain, right? which means it's going to be discontinuous at any of the points x, y that are on this line, y equals 4x. Okay? But it's a different kind of discontinuity. That's why I wanted to show you it. All right? If I take the limit of these, I'm not getting 0 over 0 anymore. Right? You pick one of these points, except for maybe 0, 0 itself. That's going to be indeterminate, but it's going to end up being undefined anyway. Okay, but you pick any other point on this line, like say 1, 4, right? 1 comma 4. I'm not getting 0 over 0. I'm getting a number over 0, which is something that gives a limit that's going off to infinity of some kind, right? Depends on what kind of trend the bottom is doing as well. So here's the next step further. If I were to take the limit along any of these points, the limit flat out wouldn't exist, right? This is the division by 0 that causes the infinity type of things. And not only that, but think about it this way. If I pick any point on this excluded line, like let's say I pick this point right here, if I approach it from 2 different directions, they don't even have to be parallel directions, okay? From one side of this line, the 4x could be greater than the y value. And then from the other side, the y could be greater than the 4x. Okay? So you see what I'm saying? By you get different values. From one side, from one direction, the z value is going to plummet to negative infinity. And from the other direction, it's going to go up to positive infinity. You're going to get this weird surface where part of the surface is going this way and the other part of the surface is going this way, right? All because you're dividing by some linear terms here, some things to the odds, and it's going to keep the negatives with the infinities sometimes and the positives with others. Also just because of the way the region is split up, right? So definitely still, that's the statement of continuity, right? It's going to be continuous everywhere else, right? On its entire domain, because you can plug any other point in and everything's just fine, okay? But I wanted you to notice what kind. This is a non-removable kind of discontinuity because the limit doesn't exist, okay? On any one of these points, the limit, not only is it infinite, but it's always split, right? There's no limit at each one of these points. So it's a complete break discontinuity, right? Going in different directions. Okay, discuss the continuity of square root of 9 minus x squared minus 9y squared. Well, that's just the top half of an ellipsoid, right? Right? If I put z here and then square both sides and then move everything over, right? It would be an ellipsoid, okay? Well, look at the domain. This is the domain of this function, right? I have to have this thing non-negative, right? So I have to have my domain is the set of all points x, y, such that x squared plus 9y squared is less than or equal to 9. Like this. Right? Because I have to have the inside non-negative. So in other words, what I end up with is this ellipse in the plane and everything on the inside. Well, that should make sense, right? It's an ellipsoid. It's coming out like this, right? It's like an M&M almost, right? But just the top half of the M&M here, right? Okay, so it's obviously continuous everywhere on this domain. I can plug in any of those values because I can square, I can subtract, I can multiply, I can square root as long as it stays positive, and that's what the domain guarantees. What I wanted to talk about was the different kind of points on this particular one. Obviously, it would be discontinuous anywhere outside of the domain, and that's because there's no function values out there, right? There's no limit values either, because there's no way to approach any of these points out here. There's complete non-existence of anything to do with this function outside of there, okay? So this one also is continuous on its domain, right? You'd have to have a pretty messed up function to not be continuous on its own domain, right? That's a completely different discussion in an advanced calculus topic. But, like I said, there was something else I wanted to point out here. There are different kind of points that we may discuss at different times in the semester, okay? When you have a set like the domain here, you have three different types of points. You have interior points, right? Like this one. If I pick this point right here, it's not on an axis, it's just somewhere in the domain. This is what we would call an interior point, right? It's interior, it's inside the domain. So of course, if I pick any point, out here, or out here, or out here, anywhere, right? That would be exterior. Right? We have interior, we have exterior. My handwriting is going to crap here. We have interior and exterior points, but there's one more kind. If you pick any point anywhere on this red curve that I've drawn, this is called a boundary point. And that's important. Okay? A boundary point defines your domain, right? A boundary point here would be where x squared plus 9y squared equals 9, would be one of the boundary points. But the way we define boundary points geometrically is also important. Okay? So let's go through the definition of interior and exterior. In the interior points, I can draw a circle at some point, a neighborhood around it. I can draw at least one circle, a neighborhood around an interior point that is completely contained inside of the set we're talking about. So notice, as the example shows, I was able to draw a circle that's completely contained inside the set, right? So that's an interior point. All it takes is one. I just need to be able to get one neighborhood inside. So even if you're right up against the boundary, there's still that little bit of space in between that I'd be able to squeeze a little circle inside of, right? And then that point would be considered interior. So with exterior, right, if I draw a circle, and if I keep drawing it, right, no matter how big I make the circle, I'll never get a circle that's inside. And in fact, with exterior, I can draw a circle around it that's completely not contained in the set. So if I can get at least one circle not contained completely inside of the set, it's all the way exterior. So I'm hoping you're seeing where this pattern's going. A boundary point is a point where no matter what size circle you draw, every single circle includes a neighborhood with a little bit of points that are in and a little bit of points that are out. Look, no matter what, if I draw a circle that's only this big, or if I draw a circle that's this big, every boundary point is going to have neighborhoods that always contain a little bit of outside and a little bit of inside. Boundary points don't have a choice. No matter how small you get that circle, it will still be part out and part in. Okay? So, what's the difference? Why are we talking about this? Interior points are the ones that we've been doing the easy limits on. Easy, right? I can plug that point into a limit, no problem, right? Therefore, easy continuity, right? Okay, exterior points, absolutely no limit. It's outside of the domain. There's no way you'll be able to do a limit there for several reasons. Also, there won't be a function value there. It's outside of the domain, hence the definition of domain, right? So, boundary points. First of all, a boundary point can either be included in a domain or not. In this case, the boundary points are included in the domain because I can plug any of these points in. It's just where this thing equals 9. Those are okay. Counterexample, look up at this up here. Technically, this is a boundary line of this domain. It's a set of points where they're not inside of the domain, right? And if I draw a circle around them, right, like this, if I draw a circle, then some of the points are out of it, right? The parts that are not included in the rest of the line here. And some are in it, the rest of the circle. Okay? Those are technically a type of boundary point, and those are not included in the domain, right? And you could start to argue something for pretty much all of them. Anywhere your domain stops, right, is technically a boundary point of some sort. Now, in this case right here, what's interesting is we may be interested in talking about the continuity of these boundary points for this function, right? So we need to talk about the limit. Fortunately, for things like this, the limit laws apply to these boundary points. I can actually take the limit as this function approaches one of the points on the boundary. Vice versa, right? The limit does not exist on these boundary points. So, of course, these boundary points have no continuity, but these boundary points do have continuity from partial directions, right? You would have to specify, okay, it's continuous from the interior, is what you would say, right? This point right here, there is continuity from inside the domain, from the interior, right? We can say it's continuous on the whole domain. The boundary points are included in that. And remember, being continuous implies that there is a limit. I can actually take the limit, and it's just like all the rest of the limit laws, it would be just plugging in values, okay? So it is continuous on everything, including the boundary for this one, but the continuity has to be specified on the boundary as coming from the interior.
So let's discuss continuity now. We had the function x squared minus y squared over x plus y. Looks a lot like a plane, doesn't it? If you remember, when we were doing our limits, we were able to reduce the calculation to x minus y. It shouldn't surprise you that if I were to just graph the plane z equals x minus y, that they would actually be one and the same, right? You can see the bottom of that one sticking out, but you can see they're really just the same plane. Okay? The reason for that is because of the part where the division by zero occurs, as we were discussing, is a set of removable discontinuity, right? In fact, the places where x equals negative y is the line consisting of this, where you can notice that that's from the domain, that's x equals negative y or y equals negative x. You can see what happens is I have this line coming down the surface, and technically all of these points are undefined. For example, I even got an example. Look, if I plug in 2, negative 2 into the function, undefined, because x and negative y are equal. Negative 10 and 10, again, x with a negative y. So if I plug those into the function, it's undefined. All of the points down this are technically undefined. But again, points are, dimensionless, and it's impossible for GeoGebra to actually show that all of these points should be actually missing, because it doesn't want to miss any of the other points right next to them, and it's hard to distinguish those. So again, it's up to us to know the difference between the plane itself and the graph that we're looking at that has the line of discontinuities. There is this line of discontinuity here, but they are removable. That's why you can't see them, and that's why we're not getting any actual breakage that's visible. Okay? Next, let's take a look at the 5 sine x over 4x minus y. Okay? That looks like this. So you can see the sinusoid starting to kick in a little bit here, right? You can see the little waviness. But take a real close look at the way it really warps up over here and then warps down, like really far down here. A lot like a vertical asymptote, right? A lot like a vertical asymptote. In fact, if I take y equals 4x, remember that makes a plane in in this 3D space. The plane y equals 4x looks like that. And if you look really closely, you can see that that plane constitutes a vertical asymptote set of points and asymptotic behavior there. It doesn't actually touch this plane ever, right? Because it can't. So it's a line of discontinuities there. And this time, it's an actual break. As you can see, sometimes it's down and up, and then on the back side it's up, then down, right? It reverses through there in a real twisted manner through the center here. But it can't touch any of the points from the domain constituting this plane right here, the line y equals 4x. All right, and then the last one that we discussed was this ellipsoid top half, right? And the domain is the ellipse as promised, where it's 3 in the x direction on either side and 1 in the y direction on either side, right? And you have this ellipsoid. I also have it in parametric form using spherical coordinates. You can see that it is actually the same shape. And it's just a little smoother when you do it in parametric, that's all. And again, the domain is that ellipse, right? And as you can see, the boundary points are part of the graph. And therefore, if I were to take a limit of one of these boundary points, I could basically just follow the curves that all lead up to any one of these boundary points, and I would have some sort of continuity that I could have coming from the interior here.
I just wanted to quickly comment that we are in multivariable calculus here, which means it's not just about functions of two variables that give back one variable. It could be functions of any number of variables. And what we've just talked about does generalize greatly to all number of dimensions. Okay? So for example, if we happen to be talking about a 3-variable function, right? Those also can be measured with limits, and we can also talk about continuity. Even if it's something that you can't visibly think of or graph, the algebraic and the definition side of it has to still have meaning. Okay? So we can still talk about it the same way. For example, all the limit laws still hold true. Just one more dimension just makes me talk about, in this case, spheres of size delta instead of circles of size delta. And then, if you go even higher, you can have hyperspheres of size delta. And it doesn't change anything in the physical definition using the distances epsilon and delta to make all these definitions. So the limit laws still hold true. Right here, the first thing you should try is plug in the numbers, right? 9 minus 1 minus 2 minus 3. I'm going to get square root of 9 minus 6, square root of 3. Okay? No difference. If I run into something with a 3-variable like this, it can just as easily still not exist for the same reason, right? In 3 variables, I'm talking about a ball, a sphere, with 0, 0, 0 as the center, and I got to be able to come from all directions and all paths, same as the other limit, okay? So if I can find 2 paths that disagree, automatic undefined, right? So do this. Follow the limit along the x-axis only. If you do x-axis only, then y and z are both 0, and I get 3x squared over x squared, which is just equal to 3. But if I do either of the other axes, like do just the y-axis, right? Something like this, then x is 0, right? I'll have 0 over y squared, which is 0. So automatically this is undefined, right? I've got 2 different paths, 2 simple paths that give me 2 different values for the limit. So obviously this limit doesn't exist, okay? Continuity, like I said, works the same way. You start by finding the domain and then just making sure whether or not you're going to include the boundary and things like that, and any other special, really weird points. But most of the stuff that we look at is pretty straightforward, and you're supposed to already know and be familiar with where do these things fail to work. 5 is a number. It's going to work everywhere, right? X works everywhere. There's nothing wrong with multiplying by x. But what about tangent? Tangent does have asymptotes whenever used to graph and trig, right? Whenever the input of tangent is some odd multiple of pi over 2, right? You have the tangent of pi over 2 is undefined, the tangent of 3 pi over 2 is undefined, or negative pi over 2 is undefined, right? All of those things. Okay, so what's our domain here? Our domain is the set of all ordered triples that are in our real 3-space system, such that x can be anything. Obviously no restrictions on x, but y plus z cannot give a bad value to tangent. And remember, where that starts is pi over 2, right? But then it's odd multiples of pi over 2. So it could also be 3 pi over 2 or 5 pi over 2. So what we do to represent that is I multiply this times 2k plus 1. And then I say that right next to this, that k is any integer. Right? And what that'll do, the 2k plus 1 will give me all odd values, right? If I plug in, say, k equals 0, which is an integer, I'll get 1 times pi over 2. Can't have pi over 2. If k is, remember, integers can be any whole number. Let's say k is negative 5. 2 times negative 5 is negative 10, plus 1 is negative 9. Negative 9 pi over 2. No good, right? So this is the domain of that function. Y plus z can't be one of those values. But as long as you're not on one of those values where y plus z is equal to that, right? It's entire sheets inside of the 3D system. Then this function works and is continuous, right? So continuous on this domain. In other words, it's continuous everywhere, but not those particular sets of values where y plus z is any one of those odd multiples of pi over 2. Okay? So don't think that we were just studying 2 variable functions. We were studying multivariable functions, and the same thing is going to be true as we push on into this course. A lot of the things that we study, we'll be doing both 2 variable and 3 variable functions, but in the back of your mind, keep reminding yourself, this would also work for a 5 variable function or a 10 variable function, whatever the situation might call for in the future. Okay? So I hope this helps you understand your functions even better. Stay tuned. The next lecture, we actually start doing some real calculus and partial derivatives.